Hi everyone, today I'd like to start our session with series compensation. Previously we learned introduction to fans and thereafter shunt compensation. In today's session, we'd like to start our parts with series compensation here. Yeah, these are the contents we have to cover in this particular session. Principles of series compensation, types here, GCSC, TCSC, TSSC configurations and their characteristics, control and applications wise. If they pose some question maybe like this, what are the objectives of series compensation or applications of series compensation means you have to write this part. Yeah. In series compensation, reactive bar is inserted in series with the transmission line for decreasing the effective transmission line impedance and thereby it improves the power transfer capability of the line. It is mostly used in extra and ultra high voltage lines. We all know one formula P equal to EV by X sine delta now. If I would like to reduce that X, there I can improve the things of active power. Remember that basic formula. And what are the advantages of series compensation is nothing but it increases the transmission capacity, improves the system stability and control voltage regulation. These are the advantages of series compensation. In which location I'd like to place series capacitor is nothing but I can place at the sending end side or receiving end side or at center of the line. Sometimes we may place it 2 or 3 more points of the line also there. That doesn't matter. Depends upon the economic considerations and technical point of view. I'd like to choose these locations. This one is a one more application or object of this series compensation. It increases the power transfer capability. How I'd like to explain with the help of on two machine system, sending end and receiving end, and the reactance carrying here is X. Let it be XS and X are receiving and sending end reactance values. Initially, I don't want to place any capacitor right now here. At that time, the power transfer here is P equal to Vs into Vr by XL into sine delta. When I would like to place one capacitor here, and there is some change in the part of power that it is Vs into Vr by XL minus Xc. Try to replace that XL with the help of Xc. What's that? Xc is nothing but reactance. L stands for inductive reactance. Xc stands for capacitive reactance. Yeah, these are the two powers we have. Initially P1, the next one P2. Try to make it some ratio here. P1 upon P2 is equal to XL by XL minus Xc. Try to make it common XL and cancel out there. We can have some formula 1 upon 1 minus K. What's that K stands for? It's a ratio of Xc to XL. It's nothing but degree of compensation. How much compensation I would like to insert, that it can decide with the help of this formula K. And try to remember in practical the K value lies in between 0.4 and 0.7 is the best value. If I'd like to choose K equal to 0.5 means in terms of percentages that it is 50%. Try to make it P2 by P1 is equal to 1 upon 1 minus K, that it is 1 by 1 minus 0.5. It's obviously, what's the value here? It's obviously 2, that it is the power becomes double. The power becomes double here. Try to remember that thing. When I would like to plot one graph in between power versus load angle means let it be initial power here is P max and the K degree of compensation here is how much? 0%. If I would like to make it the compensation K equal to 50% means degree of compensation is 50% means the entire power will becomes double, increasing the power value. Yeah, observe that thing. Next one. In terms of voltage stability is also one more point here. Series capacitive compensation can be used to reduce the series reactive impedance to minimize the receiving end voltage and the possibility of voltage collapse. Try to remember only one point here. Voltage stability in the sense I would like to make that entire voltage in 1 per unit situation. For that sake, if I would like to choose shunt compensation means the entire voltage can make it to unity if and only if the condition it supplies reactive power demand. Whereas in series compensation, it can occur with the help of reducing the line reactance value. That it is reduction in the reactance value. Originally this one is X. When I would like to place one capacitor here means the entire effective reactance will reduces and there it improves the voltage. And within the limits of voltage we can maintain here. That thing is nothing but voltage stability point of view. That it is one more application. Next thing, improvement of transient stability. Transient stability, we all know power angle characteristics. I would like to apply equal area criteria here. That it is A2 is obviously greater than A1. A2 stands for decelerating area, A1 stands for accelerating area, and the power here is V square by X into sine delta. When I would like to make some compensation here, the entire transmittable power will increases. The entire transmittable power will increases if I would like to have some degree of compensation here. Yeah, these are the two curves for without and with compensation. Next thing, power oscillation damping. Try to differentiate that load angle with respect to time. If it is greater than 0 means the electrical power transmitted must be increased, and obviously that K is maximum value here. When it is less than 0 means it is reduced and the K value becomes 0. And there I can improve the things of power oscillation damping here. Electrical power transmitted is increased if and only if the differentiation of a load angle becomes greater than 0 and K value is maximum means we can have this maximum power. This is one more application of series compensation. Next, going to the types of series compensation here, we are having some two categories, variable impedance type and switching converter type. In variable impedance type, we have to follow GCSC. GCSC stands for GTO thyristor controlled series capacitor. TSSC stands for thyristor switched series capacitor. And finally TCSC stands for thyristor controlled series capacitor. These are the categories you have to learn. The first and foremost thing, GCSC stands for GTO thyristor controlled series capacitor. It's nothing but it is given by Faraday. It consists of a fixed capacitor in parallel to GTO thyristor walls. Try to remember only one thing. What is the main difference between GTO and thyristor? That it is, if I would like to choose GTO means, that it is, let it be I would like to make it some angle gamma is equal to 30 degrees means, at that point of 30 degrees only, that GTO will turn off. Whereas in thyristors, if alpha equal to 30 degrees means, at 30 degrees only the thyristor will on. That's the main variation in between these two things. One thing is off, another thing is on. If you observe this thing, back to back GTOs in parallel to capacitor. This one is series capacitor. Back to back GTOs. GTO, it's a cross mark. Don't forget that cross mark. If GTO is on position means the entire current can travel across this one and the voltage becomes 0. Yeah, observe this particular one. Capacitor in the sense current leads voltage, CIV, current leads voltage. If the entire gamma, I would like to make it 0, at the time the total, that it is the entire capacitor voltage is maximum. If I would like to make it some angle of gamma, at the time before the value it is in on position, when it is gamma I would like to choose that entire thyristor will be, GTOs will becomes off and the voltage will carries across this thing, that it is VC value across the gamma. If gamma becomes 0 means the entire maximum voltage will be there. These are in off position. Different gamma values means the thyristors will off. Before the parameter it is in on position. This one is a graph they have did. Current leads voltage. Gamma equal to 0 means maximum voltage across the capacitor. If gamma equal to gamma 1 means the entire before the part the GTOs is in on position. After the part the GTOs is in off position there. When I would like to place one different gammas, that one is nothing but it's a principle of turn off delay angle control. They can control this entire thing via the part of different gamma values. If I would like to place one gamma equal to 30 degrees means that 30 degrees the GTOs will off. GTOs will off. That thing we have to observe. Before the part that GTOs is in on position. That's the main variation. This one is a graph for GCSC. Observe this particular thing. I equal to C dV by dt now. In this particular category, that current is fixed. The voltage will vary the parts. That current is equal to I cos omega t. V equal to 1 upon C integral I dt. That it is I by omega C. Try to substitute omega t and gamma here. It can vary the values from 0 to 90 degrees. And the fundamental capacitor voltage here is this one. I upon omega C, this one is the value. Same effective capacitor impedance we also having some formula, that it is V equal to Ix now, X equal to V by I cancel out. We can have some 1 upon omega c. This one is the value. This one is some simple mathematics. Don't bother about this thing. When I would like to plot one graph in between VCF to the part of gamma, we can have some substitute that values. If this one is for the part of 90 degrees, it's unity and it's exponentially rising and becomes 0, 1 minus 1, it becomes. This one is exponentially decaying and make it to 0. Yeah, only simple line. When the GTOs are in off position, the maximum voltage will carry across this particular thing. When I'd like to make it some gamma values means up to that the GTOs are in on position. When I'd like to give it some gamma value means those are becomes off. That thing you have to understand. Yeah, this one is a particular graph for the part of VI characteristics. Try to make it. This entire GCSC all comes under the fourth quadrant. Fourth quadrant. Don't forget that thing. Yeah, fourth quadrant. VCF stands for compensating voltage. Gamma stands for it's a turn off angle, delay angle. If I'd like to make it, two modes will be there. One thing is nothing but voltage mode. Another one is nothing but impedance control mode. Try to remember two modes. Impedance compensation mode. That it is when I would like to plot one graph maybe like this. I and V. That it is capacitive only now VC. I maximum, I minimum. Up to the level of I minimum, the entire current, the entire voltage is passing from origin. That it is straight line maybe like this. Up to minimum current. When beyond the level of minimum current to maximum current, the entire voltage will becomes constant. One thing is nothing but impedance control mode. This mode is impedance control mode. Or else in terms of other names, reactance control mode, another category. This one is reactance control mode. That it is I and VC. It's a straight line passing from origin, but it up to the level of maximum reactance. That it is XC is nothing but capacitive reactance. Two modes will be there now. One thing is nothing but reactance control mode is nothing but this one, B1. What's that A1 stands for? Voltage control mode. Voltage control mode is nothing but up to minimum current, that entire voltage stands straight line passing from origin. And minimum to maximum, it's a constant. This mode is nothing but voltage controlled mode. Don't forget this graph. This one is nothing but reactance controlled mode. Yeah, next one. When I would like to place, this one is nothing but how I would like to reduce the harmonics in this particular graph. That it is by making this GCSC blank sequentially. What's that sequentially stands for? I'd like to make it all the GCSCs in 4 series combination. If I'd like to use some MGTOs means, MGTOs combination means, I'd like to have some M-1 capacitors here. Yeah, in thyristors, I may use transformers for harmonic reduction. Whereas in GTOs, there is no option. We have to control that harmonics with the help of capacitors itself. That's the main difference. Observe that thing. These are the graphs. That the first cycle, this entire waveform may be like this. For the second cycle, up to this level. Third cycle, this one. The harmonics will be reduced. Finally, it can nullify. From these graphs, observe only one thing. If the GTO sets is M means M-1 capacitors I would like to use. There is no option for the part of transformers in GTOs. That's why I would like to place the entire reduction will be done with the help of capacitors in connected in series, and the total voltage here is it's a summation of all this voltage across the capacitors. Yeah, this one is nothing but sequentially to achieve harmonic reduction. This one is for the part of harmonic reduction. Next another one, TSSC stands for thyristor switched series capacitor. Yeah, everything is common. Try to make it capacitors in a series combination, back to back thyristors. Only changes back to back thyristors here. Previously those are GTOs, cross mark. Remember that thing. Yeah, a capacitor is inserted by turning off and it is bypassed by turning on the corresponding thyristor walls. Yeah, previously thyristors are different angles, it can on or off all can happen. Whereas in this one, at particular angle, firing angle, the thyristor will be in on position. That's the only variation. Observe this particular one. Yeah, this one is a particular diagram. Don't forget, thyristors are only straight line. GTOs, it's a cross mark. Yeah, in the capacitor, current leads voltage now when switch is in on position. Switch is in on position. That it is, this one is on position. Is there any voltage in this particular one? No, this is an on position means the entire capacitor voltage will become 0. After that I would like to make it this entire current becomes 0 means current becomes 0. Initially that current is maximum across this one. When current becomes 0 means I'd like to when current becomes 0 means the entire capacitor voltage, this voltage will becomes double the part. Remember, current becomes 0. At that time, I would like to turn off this entire part of thyristors and the entire voltage will double the part up to the level of 2 cycles. That it is one negative cycle, one positive cycle. This entire capacitor voltage will double. 2 cycles it has to cover. And there again this VC becomes 0 now here. At that time again the thyristors will on. Up to now the thyristors is in off position. That's why we can come across total voltage across the capacitor. This one is the graph you have to observe. When SW is in on means this is in on means this entire there is no voltage. When this is in off position means the entire total voltage will be accumulated here up to 2 cycles. Yeah, SW is allowed to turn on at VC equal to 0. Again it has to on means VC becomes 0. At that time I would like to apply firing angle in order to start. That thing you have to observe. But there is some drawback for this particular one. When I would like to plot one graph maybe like this. Two modes, voltage controlled mode, this one, current reactance controlled mode. Reactance controlled mode is nothing but it's a straight line passing from origin, that it is XC max, but don't shade this one, it's a switching. Don't shade this one, it's a switching. Up to minimum it's a straight line, but in terms of steps it can occur. In terms of steps wise we can have some variations in the part of this one. Yeah, in order to nullify a smooth conduction of voltage, I would like to go for the part of next criteria. That one is nothing but TCSC, thyristor control. How I'd like to control in order to make that entire voltage in a smooth way, I'd like to place one reactance here. Everything is common, capacitor, back-to-back thyristors, but I'd like to place one extra term here as inductance L. Remember that thing. Yeah. This one is a graph for the part of, for the smooth conduction of this voltage only, I'd like to have this one. It's a current limiting device, L. Current limiting device. When I'd like to have these two parts, we can have some XL reactance and this one will have some XC reactance. When these two become 0, that condition is nothing but resonance condition. There is no voltage. Two modes will be there. One thing is inductive, another one is capacitive region. In inductive region, it's a graph plotted in between the part of XC to the part of alpha, firing angle to the part of alpha. 0 to alpha limit, we can increase exponentially like this. Yeah, from that point that it is, this region is nothing but resonance region. From that alpha limit values to the part of pi by 2. The entire graph is in between the 0 to pi by 2 only here. But in between these two regions, we can have some two modes. One thing is inductive mode, another thing is capacitive mode. Inductive mode is in between 0 to alpha minimum, alpha limit value. Alpha limit value to the part of pi by 2 is the capacitive region. Try to remember this graph. This one is for the part of which thing? TCSC. Controlling can be occur with the help of this inductance that carries some current of IL at an angle of alpha. Alpha is the firing angle in thyristors. Gamma is the angle, turn off delay angle in GTOs. Negative voltage will be there in this particular one. Yeah, observe these curves also, that it is nothing but VL first quadrant, VC is in the fourth quadrant. But remember this entire, one more point, this inductive capacitive is obviously less than capacitive reactance. Inductive reactance is obviously less than capacitive reactance, that is one more condition. When I'd like to plot these curves here, alpha equal to 0, we can have some shading part maybe like this. Whereas in this particular one, we have some large area. Why means, I told one point, XC value is obviously greater than XL value, that's why its shaded part is higher. Same, this mode is nothing but voltage controlled mode and this one is nothing but reactance controlled mode. Up to the level of minimum maximum will be there in this particular one, whereas this one only maximum current. Don't forget, try to shade this maximum value for capacitance region only there. Minimum for the part of inductive. Don't forget that line. Yeah, this one is a controlling strategy here. TCSC controlled strategy for the sake of synchronization. In order to turn on this entire part of thyristors gate pulses, I'd like to give it gauge pulse generators. Yeah, how I'd like to give it is try to make it some current, and thereafter before the part current to delay angle converter is there. Synchronization purpose I'd like to use timing circuit here. All these things I'd like to generate some gate pulse generators. There I'd like to connect it to the thyristors will have some gate pulses. I'd like to give this gate pulses to this particular one. And reference values I'd like to give in capacitor reactance VC value reference. And if there is any error means and try to make it the output here as IL. That IL I'd like to give it to current to delay angle converter. There I'd like to give it to gate pulse generator. That pulses I'd like to give to gates signals from the thyristor walls. This one is nothing but control scheme for TCSC. Whatsoever the condition, this entire TCR gating control is same for everything, controlling purpose. This one is in terms of another based here, capacitor voltage 0 crossings. This one is also same, but another criteria. And finally, we land upon the things of SSSC. SSSC stands for static synchronous series compensator. There are three main components: VSC, transformer, energy storage. Energy storage provides voltage across the DC capacitor and compensates for losses. Transformer, it couples the SSSC to the transmission line. Main component here is voltage source converter. Yeah, this one is a particular diagram. One transformer. What's the main intention of SSSC is nothing but it can mainly it can have some impact on the part of active and reactive power control can happen with the help of SSSC. That's the main intention. VSC here, and I would like to connect it to the part of some capacitor, and this one is energy stores. For the controlling purpose, I would like to give some power reference and active and reactive power reference. Active reference is nothing but resistance. Reactive in the sense reactance. Yeah. What is the main need for active and reactive power flow control? Reactive power flow is unwanted power which decreases the efficiency of the transmission line. Due to the reactive power, many harmonics are existed in the power system. Hence, I would like to control this reactive power flow. Reactive power flow is an unwanted power, but it reduces the efficiency of the transmission line. That's why I would like to control this reactive power. Active power flow control is required to supply the rated power load to the demand. Yeah. What is the need? Need means I would like to control that reactive power in order to increase the efficiency of the transmission line. Next. Try to observe this particular diagram, two machine system. First slide itself. When I would like to place one capacitor means there is some reduction in the effective reactance. There it improves the power. But in terms of another diagram, they can explain here. Transmitted power is V square by X equivalent sin delta. What's that X equivalent? XL minus XC. This one is the formula. XC by XL, XC is nothing but, can I write this one maybe like this, that it is V equal to IX. That thing VQ is equal to I into X. That it is divided by I. That entire formula is active power formula is V square by X into 1 minus VQ by I. This one is the formula. Try to make it XL minus XC means XC is nothing but this one. VQ by I. I would like to replace. I would like to insert one source here, that it is series capacitor that can carry some voltage of VQ. Yeah. Try to observe. If I make a phasor diagram in between the things of VS and VR, we have some angle of delta. When I would like to place one voltage source here, it can have some some voltage here, that it is VQ, and the effective voltage will becomes reduced and the sending end voltage will drop. Initially this one is VL. There is some impact on the part of extra thing, that it is when I would like to choose VS plus VQ means this one is effective voltage VL. All VS, VR, V, all these are same initially. And when I would like to place one thing here, there is some impact on the part of which thing active power. When I would like to plot one graph here, depends upon the degree of compensation, the center voltages will increases. The center power will increases. K equal to 0, K upon 1, 1 upon 5, 1 upon 3. The center power will increases, double, everything can happen. Normalized power values. When I would like to go for the part of, if I would like to choose some different voltage values VQ, that it is, we can go beyond the level of negative power also there, negative values also here. By changing the values of which thing? V value, VQ value. That it is, if I'd like to go for negative values of VQ or positive values of VQ, that VQ is nothing but insertion of this voltage in this particular line. Yeah. Finally, we land upon this graph here. Observe this graph. How I'd like to control and reversal of power will flow takes place means no compensation. That entire line phase voltage is nothing but V and I is in phases like this. Compensation for the positive power flow. It's almost compensation. Voltage and current are in same mode. Compensation for negative power flow in the sense, if it is a positive voltage means negative current will be there or opposite direction. That it is current is in the opposite cycle to the part of voltage. That it is compensation for negative power flow. This diagram is for the part of how we can reverse real power flow. That it is initially no compensation means that entire active power is in the positive cycle for the part of no compensation and positive compensation power flow. Whereas in negative compensation power flow, that entire active power will becomes negative. Whereas initially the reactive power is obviously in negative generation wise. But when I'd like to make it compensation in negative power flow means it becomes positive. That thing you have to observe. Initially P is in the first two cycles positive and it becomes negative in negative power flow, opposite manner. That thing you have to observe. Finally, injected phase A voltage. It's obviously same, no compensation in the sense. Compensation for positive cycle means it is increasing, but compensation for negative cycle means it's obviously rising the things. That inner waveform. VQ will increases beyond the level. That it is how I would like to inject VQ. That impact will be there. Whereas injected Q in the sense, initially no compensation means there is no Q. For positive means it's obviously some negative value, and below that injection of this Q is it's some more negative value. That thing we have to observe. Yeah, these are the equations of this particular one. VQ is nothing but that's a source I would like to inject in the SSSC. This one is a control range for V and volt ampere rating of SSSC. That it is, it covers both the quadrants of 1 and 4. That it is VL max this one, VC max this one. Try to shade it this part. Why means it's not a switching. I would like to shade this center part maybe like this. Yeah. Thank you for watching. Please subscribe to my channel. Thank you.